tell us about steam reforming of ethanol and the pitfalls there. And it's a contribution from Ohio State University.
As we have seen during this previous part, he has really managed to combine surface science with reaction engineering in the most seamless manner, and has proven that fundamental research definitely has a place to play, has a role to play in industrial catalysis. So he has certainly paved the way for many new generations of researchers to follow on that path, and he continues to be an inspiration for all of us. And I'm greatly honored to be part of the celebration, and congratulations. Let's see if my remote will work. Yes. So I'm going to focus on ethanol steam reforming over cobalt catalyst supported on nanosteria, and I will focus on the oxidation reduction behavior of the metal and the support. Because what we have seen over the years is that the oxygen mobility of the support is a key factor in the catalytic performance. So some of the results I will summarize, go back many years. But one of the earlier, part of the earlier studies we had was looking at the oxygen mobility of the support. We compared different supports. Cereal is one of them, using isotopically labeled oxygen exchange experiments. These are also referred as SISICA experiments, steady-state isotopic transient kinetic exchange. And in these, we can follow the exchange rate of oxygen, gas-phase oxygen, with the surface and lab oxygen. So what we have seen is, here we're comparing just two supports, but we have many others to look at. Exchange of oxygen increases for Syria. And actually, if you look at the exchange temperature, if you go to real high temperatures, like 550 degrees centigrade, you could essentially exchange almost 100% of the oxygen that's available in the labs. So the oxygen in Syria or cobalt supported on Syria is very readily accessible. So if you look at the reduction oxidation behavior of the cobalt species, if you look at some of the pre-treatment conditions, here we're starting out with a Syria support and a simple incipient weightless impregnation using cobalt nitrate. We are looking at the calcination process in situ using laser round spectroscopy, and then we start out with the nitrate species here from temperature, and then by 250-300 degrees centigrade, nitrates get decomposed, and then if you look at the metal oxygen vibration region, this is the reference CO304 and black Syria, and we start seeing cobalt 304 forming around 300 degrees centigrade. If we do reduction, again these are reference standards, we are starting out with CO304 and then around 300-400 degrees centigrade. Most of the reduction has been completed. Another thing to note here is the band that corresponds to Syria is also getting weaker as we increase the reduction temperature. We also wanted to see how the cobalt species were changing during ethanol steam reform. Our pre-treatment involves a reduction step with hydrogen at 400 degrees centigrade. But we wanted to see whether the cobalt species would go through this reduction in situ without any hydrogen involved. So we looked at using in situ X-ray diffraction under ethanol steam reforming conditions. This is a fully oxidized catalyst. Here we're starting out with a pristine sample and then increasing the temperature in ethanol steam reforming medium, and we start seeing reduction under ESR conditions. And then if we actually look at the pre-reduced catalyst, Interestingly, we're starting out with the reduced catalyst, you can see the metallic fraction line here. But as ESR continues, there's some partial oxidation of the cobalt species. At this point, we started looking into X-ray absorption spectroscopy experiments in collaboration with Dr. Jack Miller at Barnard National Lab. This is a setup of the system where we can do in situ experiments in the beam line. So we are looking at again under the multi-reforming conditions. We're starting out with a pre-oxidized catalyst. This is the pristine catalyst. This is essentially CO2. We're looking at the cobalt KH. And then as we increase the temperature, we can see that the reduction is beginning to take place. First we form some COO, and then around 450 degrees centigrade, we have metallic, and at 500 degrees centigrade, most of it is in metallic state. Now, if we start out with a pre-reduced sample, again, we're starting out with a mixture again. This is mostly metallic, around 62% metallic. And as we start the ethanol steam reforming at 350 degrees centigrade, as you can see, there's some partial reoxidation. And it is because underwater, you can reoxidize these cobalt species. As we go higher in temperatures, at 500 degrees centigrade, actually, if we compare them, whether you start out with a fully oxidized catalyst or fully reduced catalyst, at 500 degrees centigrade, the oxidation states are remarkably similar. We also look at the magnitudes. This is at 350 degrees centigrade. As you can see, they will have different. I've skipped many slides because I had too many. But if we were increasing the temperature to 50-degree increment. But if we just jump to the 500 degrees centigrade, by the time we reach 500 degrees centigrade, the schedules are remarkably similar. So regardless of the pre-treatment conditions, the local formation environment and oxidation state both are very similar under reaction conditions. And if you look at the effect of pre-treatment on steady state activity, here we're starting off with pre-reduced catalyst and pre-oxidized catalyst, where this pre-reduced is initially much more active, but by the time you reach 500 degrees centigrade, the performances are very, very similar, and that's also the case at 500 degrees centigrade. Both hydrogen yield and product distribution are very similar. So clearly, oxygen accessibility plays a significant role in promoting catalytic performance. But also, cobalt species go through this evolution, partial oxidation, and reduction under steady-state conditions. We also wanted to see if we can study the kinetics of cobalt reduction using two different techniques. One is referred as quantitative isothermal reduction, and actually this term was coined by one of my former graduate students, Dr. Umit S.Ozkan, who is sitting at the back. So in this case, we're basically using a first-order reduction kinetics assumption, and we're following the reduction using an online method, looking at the water signal and observing it as a function of time, because this whole thing is steady-state isothermal. So using first-order kinetics, we can go through the kinetic analysis, and the first step is very fast, so we're really focusing on the second step. The analysis starts after the cobalt oxide is formed, and in the second oxidation step, we can get the regions up front and get an activation energy for cobalt oxide to cobalt metal reduction around 29 kilojoules per mole. Now, we have another technique, a complementary technique, which is referred as the Fischer-Tropsch technique. Actually, it goes to the 1950s. And here we're changing the heating rate in the temperature program analysis. In this case, it's a TDR technique. And from that, we can get an activation energy calculation. And again, remarkably, it's very similar to 29 kilojoules per mole. That's the reduction of cobalt species from +2 to metallic cobalt. Now, if we look at the oxidation, this is under oxygen. We are doing again a Kissinger experiment, and apparent activation energy for reoxidation with oxygen is around 20 kilojoules. Now, we have also done reduction oxidation cycles using X-ray absorption spectroscopy, and these are the cycles, reduction oxidation cycles, looking at the cobalt K edge at different temperatures, 350, 400, 450 degrees centigrade, and then we can quantify for each of these cycles the degree of reduction of the cobalt species. And again, we can get that for both the reduction cycle and oxidation cycle. But keep in mind that the oxidation here is with water, reduction is with hydrogen. And water is clearly acting as an oxidant for this system. And if we do the kinetic analysis, the apparent activation energy for the reoxidation with water from metallic cobalt to +2 oxidation state is around 37 kilojoules per mole. So what this phase of the study told us was that all these techniques are still complementary. Oftentimes they reaffirm the data that we get, for example, in the reduction cycle. Very similar data, and the oxidation and reoxidation with water or oxygen, we got, of course, different values. So clearly we can, these cobalt species are very dynamic species. They are never staying as they are. They are continuously going through this redox cycle, and water can certainly do the reoxidation. So at this point, we start looking into the effect of particle size on the reduction characteristics of cobalt. And we are looking at two very different series of force. One is what we would refer to as nanoparticles or nanoparticles. It is prepared by a sol gel technique. And then once we have the support, then we have incipient wetness for impregnating with cobalt. The second cycle, we wanted to go as far away from the particle size as we can do a commercial support. And if we compare the particle sizes, looking at the images, these are along the lines of 140, 160 nanometers in diameter, and the nanoparticles are around 3 to 5 nanometers in size. If we look at the X-ray diffraction patterns of these two series, of course, this is without any cobalt impregnation, there is no morphology differences. So the relative intensities of the bands, the diffraction lines are very similar, but of course they have higher uniformity in the larger particle size sample, which we will be referring to as microparticles or MP. So again, we're looking at in situ X-ray absorption analysis, looking at the cobalt K edge. This is the Zane's data. So we are comparing microparticles and nanoparticles in oxidized state. We have just CO3 boys that are fit here. After we reduce them with hydrogen at 400 degrees centigrade, there is significant reduction, but the nanoparticles, the cobalt, which is supported on nanoparticles, the degree of reduction is higher than cobalt, which is supported on microparticles. If we look at the Zane X-axis data, again, there is some difference, especially in the coordination, environment coordination number of these two types of species. If we look at the steady-state data, well, first of all, cobalt, which is supported on nanoparticles, is more readily reducible, but there's also differences in the activity. Cobalt supported on nanoparticles is more active, it has a higher hydrogen yield, as you can see here. But another feature which was very surprising to us was a significant level of ethylene yield over nanoparticle-supported cobalt catalysts. catalyst, which is supported on microparticles, essentially died, but nanoparticle catalysts kept the same level of activity with hydrogen here. So what was happening was very significant levels of coating. We could see in the post-reaction PM images, you can see the carbon fibers growing, whereas the nanoparticle sample does not really have any carbon formation. If we do again a post-reaction temperature program oxidation, this is following envelope steam reforming after 12 hours, we see a very large carbon dioxide peak and an oxygen reduction peak, showing us that we have significant carbon formation, and it was also very big carbon. There was some carbon formation, much smaller, about an order of magnitude less than we quantified it, but it was more homologous carbon. Well, ethylene steam reforming, we wanted to see what was happening with ethylene, because clearly when we had that much ethylene, why weren't we getting more coating on the nanoparticle catalyst? When we do just ethylene steam reforming, first of all, the catalyst, which is supported on nanoparticles, is not really very active. It's not doing much of the carbon-carbon bond breakage. But the microparticle samples is more active. However, at 450 degrees centigrade, the catalyst dies, and there was really the reactor clogged because there was so much coating from the catalyst. So what we're finding out here is over these nanoparticle supported cobalt catalysts, we do form ethylene, but it doesn't go to the next stage, which is the coating of the catalyst, because the conventional wisdom is that if you have dehydration, if you form ethylene, and then the next step is the coal formation. But on these catalysts, that was not the case. But the larger particle catalyst had that phenomenon occur. Well, how about the Syria so forth? So far, we haven't said anything about what is happening with the Syria. Is it just an inert support, which doesn't change? But as we have seen in one of the earlier slides, neither the catalyst nor the support is really a stagnant phenomenon. It is very, very dynamic. So we're looking at the same two Syria samples, 3.5 nanometer, and then a larger one at 2 nanometer. And actually, we can see two major reduction features here. And when we quantify the level of reduction, we see that the nanoparticle is reducing at much lower temperatures, and the final stage maybe when we go to 800 degrees centigrade is going to be similar, but the rate of reduction is much higher for the nanoparticles. We also looked at in situ Zane's spectra under enveloped steam reforming conditions, looking at the Syrian KH. And this is the nanoparticle. We see that there is reduction of cerium. We can see cerium +3 forming as early as 250 degrees centigrade. But the Syria, which is microparticle, larger particle size, we don't see any reduction. But again, we have to keep in mind that here we're talking about bulk reduction, because clearly Zane's is the bulk technique. At that point, we started a collaboration with Professor Franklin Powell. At that time, he was at the University of Notre Dame. Now, since he moved to the University of Kansas, but he has this fairly unique capability of running XPS experiments under some pressure. Obviously, it is not really atmospheric pressure. It's around 1 torr, but it is not ultra-high vacuum, so we're really forming a layer of gas, a gas layer over the surface, so we can look at the changes on the surface under reaction conditions or under conditions close to reaction conditions. So this is one of these publications describing the setup, and this is a picture of the setup. So we're looking at quantification of cerium, and this is how the cerium 3D spectrum is deconvoluted, and we're looking at the change, looking at the peak area of +3 divided describing biological area of those 3 and 4. So these are nanoparticles starting at 350 going up to 450 degrees centigrade. And clearly we see significant reduction. This is of course looking at the surface, a few monolayers at most. So we have starting at 3% to 48%, almost half of cerium at this point is in plus 3 oxidation state. This is under ethanol conditions. If we look at the microparticles, again, we don't see any bulk reduction, but surface is clearly reducing. But of course, the reduction of the surface is less compared to what it was over the nanoparticles. There are differences on these surfaces, whether it is a large particle size or a small particle size. We have done some pyridine TPD, but I have too many slides, so I figured it out. But just a CO2 TPD, because CO2 is a good probe molecule for probing basic size. This is the microparticles, this is the nanoparticles, and you can see that there is very strong CO2 adsorption. So we have highly basic surface pyridine adsorption spectra using drips showed us that we had a very much more acidic surface of the microparticles. What is steam reforming activity of the support by itself without any metal? Well, at 350 degrees centigrade, the conversion is very low. Even 400 is pretty low, it's less than 10%. At 450 degrees centigrade, we are comparing pre-oxidized and pre-reduced ceria. For the nanoparticles, actually the conversion and product distribution become very similar. Again, under ethanol steam reforming conditions, it appears that they both catalysts or both support materials are converging to the same oxidation state. And nanoparticles are more active than microparticles. One other thing that we wanted to study, and I will only take a few more minutes, not more than maybe 2, was the effect of metal on the reduction behavior of the ceria support, because everything I have shown so far was just their ceria. What happens to cerium oxidation state when we have cobalt on it? Again, we're running in situ stains, looking at the cerium K-edge. And this time we have just bare ceria and cobalt supported ceria, but these are fully oxidized species, so we're just in an oxidized form. This is under ethanol steam reforming conditions. Interestingly, when we have cobalt, we have less reduction of ceria. First, we thought this was counterintuitive because we do expect that there will be more of a reduction with the cobalt. But when we think about it, this is the oxidized cobalt species. So initially, there isn't that much ethanol steam reforming activity. We're not forming much hydrogen. However, presence of cobalt is really activating water and is keeping cerium from getting fully reduced. If we look at the microparticle, again, the bulk reduction, we don't really see that much change whether we have cobalt or not. We cannot see any bulk reduction. But if we look at the surface reducibility, again, this is under ethanol steam reforming using in situ APXPS, nanoparticles. Again, I have another slide that will compare the numbers directly, but in the presence of cobalt, ceria surface reduces less than without any cobalt species. And this is the same is true when we have microparticles, cobalt microparticles. So if we compare Bain and APXPS data of different species, this is fully oxidized ceria, so this X value is the X ceria density or X substoichiometric ceria. So if we have fully oxidized ceria, we have obviously 2, X will be 2. We don't see bulk reduction with stains, but for microparticles, but nanoparticles shows bulk reduction. If we have nanoparticles, this is with the cobalt. If we have just pure steria, actually the level of reduction is further. And then in all cases, obviously, the surface reduction is larger than the bulk reduction, as one would expect. So if I could summarize quickly, I have no idea how much time I took, but Hans told me, don't worry, take as much time as you want. So reducibility of the steria support really plays an important role in the catalytic performance of cobalt catalyst support steria. And the nanoparticles reduce much more easily under steam reforming conditions as well as under hydrogen. The presence of cerium +3 sites leads to a less acidic surface, and this may also have a lot to do with the coating behavior of the catalyst. Ceria has significant ethanol dehydration activity and some reforming activity, but more reduced samples exhibit higher activity. And the presence of cobalt metal particles affects the reduction of the ceria support. Actually, when we start out with pre-reduced catalyst, this effect of cobalt is just reversed. So in the presence of cobalt, ceria reduce more readily. So again, we see that the activity of cobalt for steam reforming is affecting the oxidation state of ceria. So I think an important really conclusion of this study is that steria, which is a common support in many catalytic systems, it has significant reducibility as well as catalytic activity in its own right, and it is likely to contribute to the observed activities of many catalysts that are supported on steria. So with that, let me acknowledge the financial support that came from the U.S. Department of Energy. Of course, our non-national laboratory, Advanced Photon Source, OSU Campus Electron-Optics Facility, and my research group, past and present. This is really an old picture, but I don't have a new group picture, which is quite a bit larger now. So with that, thank you again, and thanks for the invitation, and again, congratulations.
Thank you for your talk and for keeping the time as opposed to some of the previous speakers. There's time for one question only. Anybody?
No question.
Yeah.
I was interested in you observe the same energy barriers for the reduction of cobalt as well as oxidation of cobalt.
Oxidation energy barrier is higher.
I thought you had 29 kilojoules.
Okay, 29 kilojoules is for reduction using two different techniques. One is isothermal reduction technique, one is the Kissinger technique. So those two numbers come from
it's consistent, but okay.
Yeah, it's kind of reconfirming the data, but coming from two different techniques, looking at the reduction. Oxidation with water, actually, oxidation energy barrier is higher, but with gas-phase oxygen, it is lower.
So do you know what the rate limiting step would be? Is that the diffusion of the oxygen or is it dissociation?
Rate determining step, especially going from metallic to +2, and we believe that the steady state form of the catalyst is really a mixture of +0 and +2 oxidation states. That may be I mean, I don't really have definitive evidence, but that may be a rate determining step because it seems to be a slower step. Going to CO3, I mean, once you go to +2, going to CO3 or 4 is not difficult, but that transition seems to be more challenging.
Okay, thank you. And then it's my pleasure to introduce the last speaker, Professor